Good morning, welcome to AP Stats. We're going over the practice quiz. What we did not go over yesterday was this last problem on the bottom of page 1. So, if you want to investigate whether liking the Blackhawks and liking the Bears are independent, one way to look at it is to ask yourself, is the probability of liking the Bears equal to the probability of liking the Bears given that you like the Blackhawks? So, the probability of liking the Bears, yes, is 0.76. So you can say, and really there's a question mark above the equal sign. Are these equal? We're not saying they are, but is 0.76 equal to the probability? Here we take out the heat gun. Let's shrink the universe down to the liking the Blackhawks sub-universe. And that we have in yellow. We shrink the red down to yellow, which is only 45% of the original. And the probability of liking the Bears given liking the Blackhawks is 0.32 over 0.45. So here's where a calculator comes in handy. So when I take my calculator and type in 0.32 divided by 0.45, we get 0.711. Okay, now here's a sentence. 0.766, or rather 0.76 equals question mark 0.711. And the answer is no. Now here's some verbiage that's required. Just gonna pull the camera a little bit closer. So, color issues here. Okay. And just to make the verbiage clear, conclusion clear, we'll bring in the calculator work so you can see the calculator work that provides the basis for concluding that the answer is no. Right there. You know, the calculator work is fairly trivial. It's not that gripping, so we'll just type it up here. Okay, so I'm giving you a script, and it's not easy to remember, which is why I'm going to type it for you word for word. Make sure it shows up. Okay, here we go. The events: liking Bears and liking Blackhawks are not independent because the probability of a randomly selected person liking the Bears is 0.76. And the probability of liking Bears given that the person likes the Blackhawks is 0.711. Had the events been independent, these two probabilities would have been equal. Okay, so that's how you justify. I mean, it said justify statistically. So I just want to get the camera in here to show this. Okay. Actually, yes. Please forgive me for this. I want to improve the script a little bit. Does not equal, it's 0.76, which, you have to observe they're not equal, does not equal the probability of liking the Bears, given that the person likes the Blackhawks, which is 0.711. So I'll read this whole thing again, just to make sure, which is 0.71. So the whole justification goes like this. The events liking the Bears and liking the Blackhawks are not independent because the probability of a randomly selected person liking the Bears is 0.76, which is not equal to the probability of liking the Bears given that the person likes the Blackhawks, which is 0.711. Had the events been independent, these two probabilities would have been equal. So you're saying what your conclusion is, what your calculations are, and then what the standard is to which you're comparing your calculations. Let's take any questions you might have on this, starting with Jasmine.
So if you just said that they're not independent because the numbers aren't the same, would you get an E or no? You have to be that specific.
Be that specific.
Okay.
We actually teach to, yeah, I mean, it's like, okay, they're not equal, so what's the big deal? So they're not equal. What does that mean? Well, what we're looking for is equality. We're looking for equality. So tell your audience what you're looking for, and then tell them what you found and whether it matches what you're looking for or doesn't match what you're looking for. That's good communication. It's clear communication. Yeah, Andrew.
Would it be appropriate to say that they are not independent because 32% of sports fans like the Bears and the Blackhawks, which shows an overlap in this statistic?
Well, independent, see, what you're doing, that overlap in the statistic shows the events are not disjoint. But the categories disjoint, not disjoint are not the same, are not identical to the categories of independent, non-independent.
Could you define disjoint and not disjoint one more time, please?
Yeah, if two events are disjoint, then there are instances that occur that are common to both events. There's an overlap. There's an overlap between the two events if they are not disjoint. If they're disjoint, then there's no overlap between the two events. So that's a separate question from whether or not the events are independent. Further questions? Now, again, I could have approached this the other way. You could have had different numbers. And the different numbers that could have appeared in this were, okay, liking Blackhawks, which was Blackhawks, yeah. So you could have compared 0.45 to Blackhawks given Bears. Wait, hold on. Liking Blackhawks is 0.45. What's the probability of liking Blackhawks given that you like the Bears? Okay, so you would have compared that to 0.32 over 0.76. And by the way, 0.32 over 0.76 is 0.42, which is not the same as 0.45. Okay, so those are the other pairs of numbers that you could have used. Yes, Thomas.
Is there a point where the two numbers would be like close enough that the difference isn't like statistically significant enough for them to be not independent?
So Thomas's question, for those listening at home or while you're out jogging, is it's basically springboarding off the fact that 0.42 and 0.45 in this example really aren't that far enough. He's wondering, is there a place where the two numbers are close enough to say that there's not a statistically significant difference between them? The answer is yes. They don't have to be exactly the same. Now, at this point in the course, we're only taking exact equality, okay? But as the course unfolds, wow, you have great vision for where this course is actually going. Because the truth is, it would be weird if they were exactly the same. And so there is a point at which we say, well, there's not a statistically significant difference between those two, and therefore we're going to but at this point for the quiz coming up, which is it's not going to be today anymore, I pushed the quiz to next week, just go for either exact equality or not exact equality.
But it wouldn't be wrong if I had said that like they are independent because there's the difference between the two.
For next week's quiz, yes, it would be incorrect. I'm not going to say wrong. That implies
Gotcha.
Morality, some sort of sin has occurred. But but it would be deemed incorrect on next week's test because we're just trying to get down. We're shooting high, and then we'll modify it as we go. Further questions on this particular problem? Okay.
That was super
Incorrect.
subtle.
What, I'm sorry?
Super subtle.
Super subtle.
Yeah.
Yeah, thank you. Now, and then the next page. So here we have the blood disease, found 3% of the person, so you said set up a tree diagram. So we did one like this in class yesterday. 3% have the disease, which implies that 97% do not have the disease. A new blood test will correctly identify 97% of the persons with the disease as having the test. So basically, we get a positive test result, 0.97, negative test result, 0.03. That's a conditional probability. And 94% of the persons without the disease, that's disease complement, will get a correct negative. So 0.94 is right here, 0.06. So great example of the kind of stuff we did in class 2 days ago. Has anyone already multiplied upper branch times lower branch to get the 4 leaves and can report to me this quadruplet of numbers? Kennedy, go ahead.
0.0291,
Yep, keep going.
0.0009, 0.0582, 0.9118.
Super. What's the probability that a person is, yeah, okay, so we did it. We did part A. Part B, what's the probability that a person correctly identified as either having or not having the disease? Okay. Correctly identified. So basically, no false negatives, no false positives. It's either correct, you have the disease, positive result, which is correct. So all you had to do on this one was really add these 2 leaves together. That's all that was required. The real challenge is how could you represent the problem analytically, or maybe algebraically? It's a slightly friendlier word, but technically at College Board they would call this an analytical representation. Even though it's not required, I want to lead you toward mastery of analytical representations of problems, changing the verbal representation into an analytical representation. So, what's the probability that a person is correctly identified? So basically, what's the probability of a positive test result given that you have the disease, or, and you just want to, yeah, this is actually a fairly, what's the probability of that happening? I'll go with my original. Or the probability of a negative test result given disease complement. And or implies we're just going to add up the cases and subtract the overlap. There is no overlap. And I guess I could have, if you had written probability of disease given complement, or would be union negative result given disease complement. That's a slightly more efficient analytical representation of the problem. And then you would go through and with the union, you would subtract the overlap. So it'd be the probability of positive test result given disease plus the probability of negative test result given not disease minus the probability of positive given disease intersect probability of, or intersect negative given disease complement, which by the way is 0. There is no, those are disjoint events, so there's no overlap between those two. So that ends up being 0, and you end up just adding up these 2 leaves. If you ever get an answer to a probability question that exceeds the number 1, you know that someone has made a mistake. Very likely you made a mistake. But I don't know what you get when you add those 2 numbers, but the answer is whatever you get when you take that plus 0.9118. Any questions on part B? Speeding along to part C, what's the probability the person who's identified as having the disease actually has the disease? Could someone give me an analytical representation of this verbally expressed problem? What are they asking for using analytic symbols? All right, Andrew.
Probability of T given D.
So what's the probability that a person gets a positive test result given that they have the disease? Is the answer provided? in order to think through this, you have to ask yourself, is it undeniable fact that the person has the disease? Because whatever is undeniably true or given to be true comes after the slash. Whatever is uncertain comes to the left of the slash. Do we know the person has a positive test result?
No.
We don't. It should, what we do know is, hold on, this person is identified as having, okay, well, hold on a second. We do know they have a positive test result. The person has a positive, this is it. That's it. You done good, Andrew.
Thank you.
So, what's the probability of P given D? Is it, oh, look at that. Sometimes,
It's
Isn't it disease given that they were tested positive?
Yeah, it is.
oh, yeah.
It should be the other way
You're
around.
right, it's the other way around. And then, which is what I thought at first, and then sorry, Andrew.
I didn't do good.
You will next time, though. So, you know what? Here's a way to think about this. The fact that the person we know that they have been identified as having the disease. That means that we know for sure they have a positive test result. What we don't know is whether or not they have the disease. So, yep, that was my fault. And therefore, the correct analytic representation is this one right here. Had this been the correct analytic representation, the answer would have just been 0.97. No big deal, just yank the number off the tree diagram. But because it's disease given positive test result, then you have a choice. You can either take the 4 leaves and set them up into a two-way table. How many of you did that? You took the 4 leaves, put them into a two-way table. I mean, that's a part that I actually like. I used to like doing what Kennedy did yesterday, and that is applying the heat gun to the 4 leaves on the tree and saying, well, we know it's a positive test result, so let's shrink let's shrink it down to just this part, to the positive test results, and take this number divided by the sum of the 2 numbers, which is correct. That'll give you the right answer. So if you just want to apply the heat gun to the tree diagram, you would take 0.0291 divided by 0.0291 plus 0.0582. That's a pretty advanced visualization. Not everyone's gonna pull that off accurately. By the way, how many of you did it that way? I mean, that is how you did it. Okay, which is fine, and that gives you the correct answer. Now, those of you who decided to take the 4 leaves and set them up into a tree diagram, you've got either a positive or negative test result, either disease or disease complement. So you take the 4 leaves, and disease positive was 0.0291. That's that leaf. A leaf is a cell, is a football. And disease negative is 0.0009. Disease complement positive is 0.0582, and disease complement negative is that last leaf of 0.9118. Now the heat gun exercise becomes saying, okay, let's shrink it down to the positive subuniverse. So let's shrink it down to just these. Say, what's the probability of disease given positive? So the mathematics is still the same. You're still doing 0.0291 divided by the sum of the shrunken universe, which is 0.0291 plus 0.0582. And 0.0291, 0.0582, 291 divided by the quantity 0.0291 plus 0.0582. So the answer to that problem, by the way, was 1/3. Let's pause and take any questions you might have on this. 1/3. 1/3 of the time, if you get a positive test result, you actually have the disease. That's disturbing. Questions? Let's call for questions. Okay, let's shift gears then. You know what we're going to do? We're going to see if we know how to do any actual stats problems. And We've been talking a lot of theory. This is a handout, we're gonna call it the, for those of you listening at home, I'll give you directions on how to locate this handout online. And screw it over. Okay, now, there's a lot of words on this. I want to steer clear of the words in the preset structure. Let's look just at the diagram. You have a colored diagram where you have this universe of college dorm rooms. Are we getting you ready for the real world or what? And some dorm rooms have, in some ways this is demeaning. It's like, oh, what, you think that we're not gonna pay attention in class unless you give us examples that have to do with eating and watching TV? I'm sorry. Yeah.
I still have a question about the last.
Oh, now, we do want to make sure we get all the questions about this thing. Your question on this is what?
Yeah, so, I'm still confused why it is the probability of disease given a positive.
Yeah, no surprise. Even I got a little bit whacked out in my thinking on that. So here's how you can straighten it out. Ask yourself, what do we know happened? Probably the person who is identified, okay, we know they've been identified as having the disease. What's the probability that they actually have the disease? Do we know whether they actually have the disease? No, we don't know whether they have the disease. The only thing we know is what the test tells us. And the test tells us that you have been identified as having the disease. That's their fancy way of saying, we know for sure this person got a positive test result. So what you know to be true goes to the right of the slash. That's the given. That's what's given. What we don't know is whether the person has the disease. So that's why this is the correct analytic representation.
Okay.
Okay? So thanks for being patient with me on that. It's, I've modeled for you the fact that it's potentially confusing. So back to the televisions and refrigerators. So you have a thing that looks like this. You've got the refrigerator. Actually, I guess it's supposed to be labeled like that. So this is the labeling for the actual Venn diagrams. This is probably what your thing looks like. Okay, what's the given information? Again, we're just ignoring this. This is scaffolding for people who don't really understand, but I think you have a deep level of understanding. You're gonna be able to figure this out. A check of dorm rooms on a large college campus revealed that 38% had refrigerators. How do we bring that into the Venn diagram? Some of you may be wondering, why are we using a Venn diagram and not a two-way table? How many of you are saying, you know what? I actually prefer two-way tables to Venn diagrams. Is anyone in the I prefer two-way tables to Venn diagrams category? Tell you what, let's just do them both. Let's master both. I want to show you how you would set it up in a two-way table. So let's say fridge, either yes or no, and TV, either yes or no. Because you never know how they're going to present it on the AP test. Who knows? They might give you the Venn diagram on the AP test. So you got to be ready for all three. Tree, Venn, two-way. So if you're doing a two-way table, the fact that 38% had refrigerators is represented by fridge yes is 0.38, right down there. In a Venn diagram, it's hard to put the number 0.38 in yet because 0.38 tells you what the whole blue circle is, the football part of the blue circle and the cookie with a bite taken out of it portion of the blue circle. So for now, usually what I do is I'll put the 0.38 sitting on the rim of the blue circle, but I'm not yet ready to divide it up between the two. 52% had TVs. In a two-way table, TV yes is 0.52, so we slide that right over there. And over here on the green circle, I'm gonna let a 0.52 sit there temporarily. I better put it in parentheses. It's like, that's temporarily what we have for the entire green circle, football plus cookie with the bite taken out of it combined. 21% had both, so that goes in the football. They're telling us the football of the Venn diagram. What are they telling us in the two-way table? Yeah, they're the upper left, they're telling us this is point 21. So I'd like you to do both. I would like you to fill in on the two-way table the other three cells and this number and that number. On the Venn diagram, I'd like you to fill in both cookies and the region outside the dividing cell shape. This is like what you looked like. This was yourself. If you took a selfie when you were just two cells, this is what you would have looked like, the dividing cell shape. Football, cookie with a bite taken out of it, dividing cells. And there's others. Okay, I'm going to begin talking you through the Venn diagram. Subtraction comes in handy here. 21 from 38 is 17. So we know this is point 17. Now I can erase the point 38. I don't need it anymore because the point 38 was broken up into point 17, point 21. This point 52, I'm going to have to subtract point 21 from that to get the green cookie with the bite taken out of it. 52, 42, 32, 31. So this is going to be point 31, so cross up point 52. Whereas over here, I do that same subtraction. You can kind of see the connections here. So this is point 31. It's got to be point 17. And I get more information in the two-way table. Point 38 has got to be point 62, because now those add up to 1. This is point 48. So now I can, point 31, that's got to be point 31. These have got to add to point 62. You can cross-check to make sure that these add up to point 48. They do. So, what is this fourth region? 1, 2, 3, check that out, point 17, point 21, point 31. So this other point 31 has got to be the dorm rooms that have, gasp, neither a TV nor a fridge? Is it legal to subject college students to that sort of deprivation? Or maybe it's freedom. Maybe it's a blessing. Any questions on how to set up the Venn diagram? So check it out, nice connection. The 4 cells of the two-way table do align with the 4 cells, or the 4 regions of the Venn diagram. And then we can answer questions. So go ahead, without paying any attention to these words, because you understand this enough that you can just answer the question. Try to get numeric answers to these 3 questions without reference to the setup. So try it. I'm going to pause the camera while you work on these. Ready, go. Okay, we're back. Now, the activity that you just did your answers can be compared to the answers that are listed there. Are there any of these that gave you trouble, you have questions about? Maybe you're wondering, how do you represent these analytically? Question, yes, Justin. B? Okay. So let's take a look at what's the probability that the person, randomly selected college student has, or the randomly selected dorm, has a TV or a refrigerator, but not both. Now the Venn diagram is kind of sweet. It's like it's point 17 plus point 31. They're talking about the 2 cookies. They have a fridge or a TV, but they're not in the football section. So here we see an upside to the Venn diagram. It's like, well, yeah, I can see exactly what they're describing. Point 17 plus point 31. Now, so here, it's kind of like saying we're going to take this, yes TV, and yes fridge. So it's like you could add these 2 numbers and then subtract the football twice. Because if you just add these 2 numbers, you're adding the football twice. So, and they don't want the football at all. They don't want any overlap. So you'd have to subtract out the point 21 twice. So that's another approach if you were leaning on the two-way table. Question or providing service to students? Make it easy for people. Any other questions on this page? All right, then turn to the next page. Oh yeah, thanks. Appreciate that. Okay. So health. No, it's not filled in. Okay, what I'd like you to do is try this quadruplet of problems using the two-way tables that are provided. And I'm gonna pause the camera while you work on these four. You may begin. We're back taking a look at these four. The column and row totals can be really helpful. Part A, probably the man has both conditions, would be 0.11, high cholesterol and high blood pressure. It's right there. It's this cell, 0.11. What's the probability that a man has high blood pressure? Just add up these. We got the 0.27 total. The probability that a man with high blood pressure has high, so we know for sure he has high blood pressure. That comes after the slash. What we don't know is whether he has high cholesterol. So we shrink the universe down, we apply the heat gun, and so now we have the high blood pressure sub-universe, and we look at the probability of high cholesterol. So it's 0.11 divided by 0.27 will give you 0.407. And what's the probability that a man with high blood pressure, if it's known that he has high cholesterol? What's the beginning of this question stem? What is the probability that a man with high blood pressure, so it's given that he has high blood pressure, okay, so it's known he has high cholesterol. And so we shrink it this way, and we take 0.11 divided by 0.32. So look at how often you use the heat gun. You see why we took a whole day and we call it heat gun day? It's like you end up using it time after time after time. Frodo.
So still, why you do it in this way instead of V?
Okay, so your question is about part B?
D.
D as in dog? Okay. So, what is the probability that a man has high blood pressure if it's known? Okay, so they're about to tell us. When you see that phrase, if it's known, they're about to tell us what comes after the slash. What is given? Probability of blank, given that, well, we know he has high cholesterol. So put that afterwards. We're going to shrink it down to the high cholesterol sub-universe.
Okay, so can I say in the situation that we are looking for, like if there should be something given by something we already know?
Yeah, that's a good way to think about it. What's contingent, or what's not automatic, what's not known comes before the slash. What is known to be true, it's a 100% probability to be true comes after the slash.
So the unknown given by known.
That's a good way to think about it. Yes. What's the probability of unknown or uncertain given certain? I'd say uncertain given certain. And then on the other handout that I handed out to you, we have the global survey. If you just take a brief look at this one. Open up to problem 5, the global survey problem. So it's a two-way table that has many cells in it. First of all, we're asking what's the probability that a person is from the United States? The given information here, you can scan through that if you want, but basically it's a two-way table. And the United States is right in here. It looks like it adds up to 1557 out of the total 7690. It feels like a Titanic problem, except with more categories. What's the probability that person completed his or her education? Okay, those are kind of trivial. The challenging problem here is to distinguish between the or problem in part C and the and problem here. Try to set up the fractions. You don't have to actually get the answer on your calculator, but try the setup for parts C and D on your own. I'm going to tour the room, see what you come up with. You may begin. Okay, as we were looking at the OR problem, you had to subtract the football to get 0.2404. For the AND problem, it's just one cell. You just had to pick out one cell in the table that showed the overlap between France and Finnish-only primary school. So I hope you enjoy your weekend. We'll see you on Monday.
Do we have a quiz Monday?
Yeah, quiz on Monday. That's a fact.